Hey people, in this video we're going to talk about calorimetry and how it relates to enthalpy and our thermochemistry unit. And so there's some introductory things that we want to talk about first. So what is calorimetry? Calorimetry is the process of measuring heat based on observing the temperature change when a body absorbs or discharges energy as heat. So let's talk about what that means. So what we can do is we can actually put something to react together and measure that temperature change. And if we can measure that temperature change, we then can calculate how much heat is either released or absorbed, depending on if it's an endothermic or exothermic reaction, and get a numerical value of how much energy we'll get out of that. If we know our energy in the form of heat from that, we then can also figure out our enthalpy, which is delta H. So remember the difference between them. Q is just heat, it's measured in kilojoules, and delta H is enthalpy, it has the moles in consideration. And so to find our delta H, we would take our Q and divide it by the moles of the reaction. And so this is a way that we can take data in lab and actually calculate our Q and our delta H. So we have a very fancy apparatus here, and what it actually is just coffee cups, right? Coffee cups, the styrofoam cups, they are very good insulators. They keep that heat trapped inside. So whenever we're measuring our temperature, we don't have any of that heat that is lost to the surroundings. And so that's what we're gonna do whenever we're working our lab with calorimetry. Now, when we say coffee cup calorimetry, that's where we use the styrofoam cup, and we refer to this as a constant pressure calorimetry. Now we're going to be doing a constant pressure calorimetry for some things, but for most things we're going to actually calculate it out, not assuming that we have a constant pressure. If you do have a constant pressure calorimeter, then I can find my Q and set it directly equal to delta H. Now for most AP problems, they don't allow this to happen. They don't assume that it's a constant pressure calorimeter. And so I'm gonna show you guys one example problem with the Q equals delta H process in these notes, and then we're gonna do other example problems without assuming that it's constant pressure, okay? And so what do we do here? Well, we have to take two measurements. The very first measurement that we have to take is an initial temperature. So whatever the temperature is before my reaction takes place. The second measurement is a final temperature. What is the final temperature after the reaction takes place? And so we can kind of figure out conceptually what will happen to our heat or energy if my temperature increases. Remember, we talked about this before in our notes. If my temperature increases as a result of the reaction, then that is an exothermic reaction. That energy is released to the surroundings, because remember, the temperature, I'm measuring the surroundings. I'm not measuring inside the reaction. So if my temperature increases, energy is released to the surroundings, and therefore that's an exothermic process. If I were to measure my initial and final temperature and my temperature were to decrease, then that means that the reaction itself has absorbed energy from the surroundings, and therefore we have an endothermic process. All right, so that's very important to know whenever we are working these things here. So here's a couple of other terms you need to know. They could give us different things to help us with our calculations. And so the first thing is heat capacity. Now, what is very important to know with these terms are the units involved. Heat capacity has these units, joules per degree Celsius. So we're gonna look at that in just a second, okay? So that is heat capacity's units. It is the energy required to raise the temperature by 1 degree. We have specific heat capacity, and I think when you guys did your introductory assignment, that one of the Bozeman videos talked about specific heat, exactly what it is. So specific heat capacity, right, these two words are different, has something else in consideration for its unit. It is the quantity of heat transferred, so joules per gram degrees Celsius. So notice how we have some unit changes here. This does not have grams into account. This does have grams into account. And then for the very last thing, we have molar heat capacity. Molar heat capacity has different units. It's either joules per mole Kelvin or joules per mole degrees Celsius. And so again, let's write these out. This is molar heat capacity. We have specific heat capacity. And we have just generic heat capacity. So why is it important for us to know all of these different things? Well, these are going to be used in our calculation for heat. So if we go to the next page, we'll see that this is our equation. Our energy, heat, released or gained, or AKA absorbed, is Q equals MC delta T. So let's talk about what each of these things are. So Q stands for heat, right? Remember that if the heat is released, Q is a negative quantity. If the heat is absorbed, Q is a positive quantity. This M right here stands for mass, right? So we measure mass in grams. So this is why our units are important here. We measure this mass in grams, okay? C stands for specific heat, right? And so the units for specific heat here are joules per grams degrees Celsius. So do you see how we're getting one of our units to cross out whenever we're doing this calculation? If grams is on the top here and grams is on the bottom here, that unit cancels out. So then we have delta T. Now it's very important for us to mathematically know what the delta sign means. Delta means change. And when we take a change, we take a final minus initial reading. Okay, change, delta T, final minus initial. So what do you think T stands for? Remember what we're measuring, our temperature. So delta T means a final minus initial temperature reading. We are doing a calculation of the final minus the initial temperatures. And that's what delta T is. So here's my question to you. You notice our units here. What units must we have delta T in order for everything to cross out properly? Well, I hope you said delta degrees Celsius, because since you see that degrees Celsius is here on the bottom, I want my degrees Celsius to be on the top there, so those units cross out as well. Notice how usually when we work with temperature in class, we're always converting to Kelvin, right? Well, if I have a specific heat given to me, because it is in the unit joules per gram degrees Celsius, I need to keep my temperature in Celsius in order for those units to cross out. And so when we do this calculation, we're basically taking our mass in grams, our specific heat, these will usually be given to you unless you have heat and you're trying to solve for it, and your final minus initial temperature. We take these values and we multiply them together. And when we do so, we get our quantity of heat, but what unit is that in? That is going to be in joules. Well, remember how we talked about when I find Q needs to be in kilojoules. So what you'll have to do is take this joules, divide by 1,000 in order to get your kilojoules reading. So just like when we were working with delta G equals negative infi, I told you to specifically write out those units and cross them out so you know what you're working with for your final answer. Make sure you're doing that for this unit as well. We write down physically all of our units, cross them out so we do not forget to convert at the very end, and therefore our unit is in kilojoules. Now, how do we take this Q and convert it to delta H? Well, we're kind of at the starting point where we were at when we were doing stoichiometry, right? Remember on some of those stoichiometry problems, you were given grams of your substance. We have a mass here, right? That's given to me. That is another piece of data that we would have to collect in the lab. And you have your kilojoules, so we're going to take our delta H is equal to Q divided by moles of your reaction, just like we did in stoichiometry. And I'll show you guys an example problem with this later on in the lab. Now, if the question says that you have a constant pressure calorimeter, that is when Q is equal to delta H only, okay? That is only if the problem says you have a constant pressure calorimeter, okay? If you do not have a constant pressure calorimeter, we have to use this approach to solve for delta H, okay? Now, notice how I plugged in specific heat, and so I took care of that, and I found out how to find Q, but I left these guys kind of hanging. I didn't say anything about heat capacity yet, and I didn't say anything about molar heat capacity. Well, when do I use these different things? It's all based upon the data that's given to you. Because in this particular instance, I was given a gram amount. That is why I had to use specific heat in this place right here, because I have to make sure my units cancel out. So if you remember that I have to get all of my units to cancel out in order to get just joules or just kilojoules by itself, because that is the units for Q, you will know when to use each one of these. So let me give you an example. Let's say, I'm going to keep these here, that you were given just an initial temperature and a final temperature reading. That's it. That's all you were given. What would we have to use here in order to get Q? Well, all I have is my temperature, degrees Celsius. So do you see how this unit here just has joules and degrees Celsius in it? So if I wanted to find my Q, if I was just given an initial and final temperature, then I would use my heat capacity times delta T, because our units will cancel out due to heat capacity being joules per degree Celsius and my delta T being in degrees Celsius. So do you see that when I calculate that, degrees Celsius is on top here, degrees Celsius is on bottom here, I'm left with just joules. So you use heat capacity, and that value will be given to you when you are not given a gram amount, okay? So that takes care of when do I solve for this. When do I use specific heat capacity? We just talked about that. I use specific heat capacity when I am given an initial and a final temperature, as well as a gram amount of my sample. So if you guys kind of see the way this works here, matching my units, making sure the proper units cancel out, when do you think I would use my molar heat capacity? Well, I would use my molar heat capacity if I have moles and temperature given to me in the problem. So how would I calculate my Q as a result for that? So if I want to solve for Q with given molar heat capacity given to me in the problem, I would take moles times molar heat capacity times delta T. So if I'm using this one here, my moles would be just moles. My molar heat capacity would be joules per mole Kelvin. And my temperature would have to be in what unit? It would have to be in Kelvin for me to get all of these units to cross out. So do you see here how Kelvin would cross out, moles would cross out, and I'm left with just joules, which is what I want because that is what Q is measured in. I would then have to convert to kilojoules, of course. What if I was given molar heat capacity in the problem, but it was in the terms of joules per mole degree Celsius? What would change here? Well, the only thing that would change is I would want this temperature reading in degrees Celsius, so now that unit is able to cross out. So when you are working with heat, solving it from a calorimetry problem, based upon what you are given in the problem is which one of these that you are going to use. Majority of the time, however, they will always give you specific heat values. But as long as you remember to match up units and try to get joules by itself, because that is what Q is measured in, you will never get this wrong, okay? Now, there is one specific heat quantity that is used over and over again, and that is the specific heat quantity of water. So you will see this a whole bunch in your practice problems. And so the specific heat of water is 4.184 joules per gram degree Celsius. So anytime in lab where we take something and mix it, and we're mixing it with water, or we're taking something and it's producing water as a product, this will always be the specific heat quantity that we know. Now, I don't think that on AP exams you would have to memorize it. I think that it's always given to you, but for labs and stuff, you do need to know this value. So make sure that you write it down in your notes. You have it in your notes because you have a note packet, don't you? So highlight it real good, okay? So that is the water is one of the highest specific heats known. So let's kind of think about that out loud, right? Whenever you saw the video that had specific heat capacities, it was the heat exchange video in the introductory video assignment. Then it talked about all these different metals that were having specific heats. Well, most metals have very low specific heat values. So let's talk about specific heats versus temperature change, okay? If I have a high specific heat value, then that means I have a very low temperature change. If I have a very low specific heat value, I am going to have a very high temperature change, meaning that specific heat and change in temperature are indirectly related, meaning when one goes up, the other goes down. When one goes down, the other goes up. So these have an indirect or an inverse relationship. So what does that mean? Well, water has a very high specific heat value. So that's 4.184 joules per gram degree Celsius. So what that means is that the temperature change is not as drastic because there's so much energy that has to be put in order to change that temperature. That's why when we go to the beach during spring break, because it's been cold all winter and the sun's finally getting out and it's starting to get warm, the water is still freezing cold. It's because it takes so much energy to change that water to warm it up. Same thing with pools. You have to have a lot of energy to put in order to get that water to actually increase in temperature. And so the temperature change is very small because you have such a high specific heat. Low specific heats, on the other hand, so like most metals are like point something specific heats. Like I think copper, this might be off, but it might be something around 0.22 or 0.23 joules per grams degrees Celsius. You see that's a very low number comparatively. These guys will have very drastic temperature changes. So if I were to put a piece of metal, like a piece of copper, and I were to heat it up, almost immediately after it's been on the burner, like a Bunsen burner or something like that, it will be very hot to the touch, right? And that's because just a very small amount of energy needs to put in to change my temperature. And so that's why these guys are indirectly related. So they might ask some conceptual questions dealing with specific heat and temperature change, especially on multiple choice. So it's very important to understand this conceptually. There's one more thing I want to talk about before we go through an example problem. So let's say we have a reaction. And so you have your reaction here, and you have your surroundings that are outside of that. My computer timed out, but we'll still go with it. So you have your reaction, you have your surroundings, right? Let's say that this reaction is going to give off energy, right? So it's going to release energy. Therefore, the reaction itself, if it's releasing energy, is an exothermic process. What's going to happen as a result? These surroundings are going to get warmer. So we are going to release energy to the surroundings, right? Our surroundings are getting warmer as a result. What does that say about our reaction versus our surroundings? If this reaction is releasing, let's just say 100 kilojoules of energy, right? If this reaction is releasing 100 kilojoules of energy, how much energy is the surroundings absorbing? Well, the answer is 100 kilojoules of energy. That is because of the conservation of energy. So however much energy is released by this reaction, that is the equal amount of energy that is absorbed by the surroundings. But what is different? It's different with the sign convention. Remember how we said that the reaction released energy, right? So what type of value will that be if we have 100 kilojoules released? That would be negative 100 kilojoules released, because that means an exothermic process. So this is what the reaction is doing. Our surroundings are gaining 100 kilojoules of that energy. And so this is what our surroundings are equal to. This is all due to the law of conservation of energy. However much energy is lost from something is going to be the same amount but opposite in sign of the energy that is gained by the other thing. And this is a very important concept to know whenever we are working law of conservation of energy problems dealing with calorimetry. And I'm going to go through a whole nother video that's going through an example problem dealing with this. So you should probably have 2 more videos that you are going to watch. The very first video is going to be about how do I work my Q equals MC delta T questions. How do I convert that to delta H? All right. The second video that you're going to watch is dealing with this law of conservation of energy problems. Now, I know that we didn't go through a constant calorimetry problem or whatever. You can work on the exercise, whatever exercise is underneath here. Exercise 5, right? This is a constant calorimetry question, okay? And so what you'll have to do for exercise 5 is find your total mass, and you can figure that out because it gives you the density there. And then you can find your specific heat, which is given to you, and your delta T, which your initial and your final temperature are given to you there as well. And when you work that, you're going to find Q equals MC delta T. Because this question says it's a coffee cup calorimeter, so we are assuming that it's at constant pressure. Whatever Q value I find is also going to be my delta H value. So I want you guys to work exercise 5 in here. You don't have to worry about the other exercise 5s or the other exercises. And then if you need any help with that exercise 5, you can let me know. So the next video is going to be what if we don't have constant pressure calorimeters, which is more so of what AP problems will be geared towards. And then the next video is on the law of conservation of energy, dealing with calorimetry, which is again what we talked about here. So I hope this video is helpful. I hope it gives you a good introduction into calorimetry, and we are going to be doing some labs dealing with this as well. Catch you later.